Alrighty, I think we'll get started. Thanks all for coming just before lunch, I know, but hopefully I'll hold your interest a little bit better than the thoughts of lunch. So my name is Callendrello. I am at Red Hat, formerly CoreOS, and I'm going to talk about Kubernetes, the CNI, and how these two interact. This is an intermediate level talk, so I'm going to assume that you more or less have an idea of what's going on, and try and get sort of technical, trying to go into some details. So so let's have some fun. Who am I? I am a Rocket developer, a maintainer of the CNI project. I'm a firm believer in IPv6, which is awesome. So this is just what we're going to talk about today. 4 basic topics plus a quick introduction. So starting out, what is CNI actually? And it's okay that it's a little bit of a confusing term because in this particular community, this term has come to mean a couple different things. It's a bit overloaded. And then another question is sort of a historical question of why is it designed the way that it is? So in this particular community, CNI means 3 different and slightly related things. First of all, and most formally, it is a vendor-neutral protocol that is used by container runtime engines to make requests to networking providers. That is, by definition, what CNI is, right? So, and it's not just for Kubernetes. In fact, it was started part of the Rocket project initially. CNI has also come to mean a set of commonly used networking plugins that are maintained by the CNI community, as opposed to the Kubernetes community or by a specific vendor. And CNI is also shorthand for a plugin for the kubelet called CNI. Oops. In other words, when you type network plugin equals CNI in the command line, the kubelet is going to run one code path versus another one. And how does it all come together then with Kubernetes? There are other talks that have outlined this a little bit better, so I'm going to go very quickly. It does these things. You write a configuration file, you put it on disk, you put some binaries on disk. At some point in time later, you use Kubernetes to create a pod. Kubernetes executes those binaries, passes this configuration file into standard in, and then your pod is online, like magic. Great. So this is the base of where we are today. As for why it is designed the way it is, if you think about every other extension point in the Kubernetes ecosystem, it's always protobuf, gRPC, daemon, CSI, device plugins, everything. So why isn't CNI like this? Why is CNI unique? Well, CNI came out originally out of Rocket, and Rocket is a daemonless container runtime engine, so it wouldn't really have matched the architecture for CNI to require plugins to be a daemon. And Rocket has always focused on really clean, really simple integration points, and CNI fell out of that effort. Additionally, as some of you may have discovered, either hopefully with the blog post or not so hopefully with bugs in production, managing network namespaces, managing any sort of namespace in Go is not reliable. And this was only fixed in Go 1.10, which Kubernetes still doesn't build with, right? So you have to use subprices. You have to fork an exec to safely manage networking namespaces in Golang. So you might as well just make that fork and exec protocol your execution protocol. So that is in effect CNI. All right, so now we all are on the same page. We all know everything. Let's talk about how CNI is used in Kubernetes. And I really want to emphasize that CNI is not just for Kubernetes. And so how Kubernetes uses CNI might be different from how other container runtime engines use CNI. Just to get some terminology really quickly, you probably have seen this, but on the right we have a node, and it has an Ethernet interface, it has an IP address. On that node is some pod. That pod also has an address and IP, and this state corresponds in the API server. It's reflected here. This is the node object, and the important things, you can see that the node has reported its internal IP, and the node has been assigned something called a pod CIDR. And this is the block of IP addresses that the node is going to use for the IP addresses in the pod. Likewise, this is reflected in the pod's data structure in the API server. It has a host IP, which is useful, and it has the pod IP that has been assigned to the ETH0 inside the pod. As you can see, of course, the pod IP is inside the pod CIDR, although this is not actually a requirement. And more importantly, the pod IP and the pod CIDR are not in the host's network interface, and this is important. This slide is for the benefit of people who have downloaded the slides and don't feel like watching through the video. Skip that. So how does CNI play into this little dance here? So when a pod is added to a node, a CNI plugin needs to do three things. A CNI plugin for Kubernetes needs to do three things. It needs to create this ETH0 inside the container, inside the pod's network namespace. In other words, it needs to connect the pod to the network. It needs to allocate the pod IP. So CNI plugins are responsible for IP address allocation. The pod CIDR is a hint. However, Kubernetes does not actually require that the pod's IP be inside the pod CIDR. And the third thing that the CNI plugin needs to do is it needs to make this pod IP reachable by the whole cluster. So in other words, a CNI plugin is expected to do two related but distinct tasks. It needs to provide connectivity to an isolation domain. In other words, it needs to put ETH0 inside this network namespace, or it could also be required to do ETH0 inside, say, a virtual machine. That's connectivity from the domain to the host. It also needs to provide reachability. In other words, this pod IP needs to be reachable to the entire cluster. Now, a question that's probably worth asking, just so we all understand why this is the way it is why do we have plugins to do this at all? And the answer is that it's a really diverse space, and everybody has quite distinct requirements for how to solve these problems. Connectivity, in other words, bringing your pod online so it can go to Google or whatever, it depends on your networking interface hardware on the host. It depends on the isolation technology that you're using, whether you're using namespaces or virtual machines. And it depends on performance requirements, and that of course means it depends on your budget. Reachability depends on your networking hardware just the same, but not your networking hardware on the host. It depends on your networking hardware inside your broader network, right? So can you touch your networking hardware? Can you touch the people who can touch your networking hardware? Is the networking hardware and are the people that can touch your networking hardware, are they yours or are they in the cloud, right? Like, there's no such cloud, it's just other people's routers, but nevertheless. How do you talk to your networking hardware? Do you talk something sort of traditional like BGP or OSPF? Do you have a custom REST interface? And of course, what's your performance requirements and what's your budget, right? All of these things have wildly different answers for wildly different circumstances. So it's natural to think that we should have a plugin system for that. Reachability really is a really rich topic. And it is important to understand that Kubernetes doesn't match sort of the traditional networking environment. Traditional networking environments, the general practices, nodes or participants in the network have long, relatively predictable lifetimes. Importantly, address allocation is semi-manual and is most importantly is topology aware. So you have a subnet for your rack, you have a subnet for your row, you have a subnet for your data center, everything is nicely aggregated. And this is the big one. For IPv4 environments, how many of you have run out of net 10, right? One interface, even if you're using entirely private IPs, one interface in your network generally equals one IP address. Till we all move to v6. Whereas Kubernetes basically flips this entirely on its head, right? It's generally IP allocation is topology unaware. There are cases where this is not the case. Generally, it's topology unaware. Kubernetes will happily allocate hundreds or more of IP addresses per node, which means that each physical port on your router infrastructure needs to be able to handle much more addressing. And lifetimes are short, churn is high, addressing is constantly changing, nodes or participants in the network are coming and going. So there really is a disconnect between how traditional networking environments work and how Kubernetes intends to use those networking environments. All this is to say that reachability is a very rich and complicated topic when you're trying to bring Kubernetes into your world. So how do CNI plugins work with Kubernetes? Let's talk a little bit more in detail. Like I said, CNI plugins need to do two things. They often have two separate components. They typically have a CNI binary, so this is the CNI spec binary executed by the kubelet that configures the pod's interface. This is for technical reasons, this is for lifecycle reasons. This is the code that is actually going to be doing the namespace switch, so this needs to be a separate process. That is providing your connectivity. Separately, essentially all CNI systems for Kubernetes also include a daemon that is going to manage routing. In other words, you're going to have a daemon that is going to be providing the reachability solution for your network. Connectivity is almost exclusively done the same way. If you're using network namespaces, you're going to create a VETH pair, which is a point-to-point virtual tunnel. Most of you have probably seen this. If not, there is an excellent tutorial by LWN where you can do this in a couple command lines. This is all entirely supported with the IP binary. So the IP binary is effectively a container runtime because you can do IP netns new. So now you have a command line container runtime engine. I highly recommend all of you just search for namespaces in operation. You all should subscribe to LWN or Linux Weekly News anyways. They are a really important source of news and a commentary for all of us in the open source and Linux community. So connectivity, almost always solved in this particular manner. Reachability is much more diverse. Reachability has one goal, which is to make every pod CIDR, which is assigned dynamically, reachable from every node in your Kubernetes cluster. Another way of thinking about this is that reachability is you need to announce some semi-dynamic routes to some peers. So does this sound familiar? Right? This is every routing protocol ever existed. This is the solution they need to solve. And essentially all CNI plugins contain a daemon that runs in the host that programs the network with the pod CIDR. However, programming the network, in other words, programming this pod CIDR can take a lot of different forms. You can program not your network, but you can program the routing tables on every node. That is an overlay network. VXLAN, IP and IP, or even no encapsulation. However, if your routers don't know about your pod CIDR, then you have an overlay network. You can program your network's routing tables via REST, in which case you are paying Amazon. That is any sort of cloud provider-based API route table manipulation. You need to be careful, you need to watch your resource limits, but this is a very effective way. It's a great way to avoid encapsulation while still having full reachability. You can also program your network using traditional networking protocols. In other words, OSPF or BGP. And some of the plugins that provide this are Calico and Romana. And this has an awesome feature where your pod CIDRs are now real addresses inside your network, and they're reachable not just internal to your cluster, but external to your cluster. But this comes at a cost. You need to have routers that you can talk to, and you need to make sure that your routers have enough memory and hardware to be able to accept the scale and churn of Kubernetes. So it's a trade-off. So an important thing to understand is why are these two separate components? Why do we have this daemon and why do we have a binary? Why we can't make them the same thing? And it really comes down to the fact that the CNI spec only covers the connectivity case. It doesn't cover reachability, but Kubernetes has broader expectations, right? So CNI has essentially two verbs. It has add container and delete container. And it only understands pod lifecycle. But route lifecycle, which is to say the lifecycle of the pod CIDR, is different from that. It's per node. So you can't get away with you have to have a long running process, right? If you have an overlay network, you already know this because you need to program every node anytime any node changes. So you have to have a daemon that is programming every node and watching every node in the API server. If you're talking a routing protocol, if you're talking BGP or OSPF, those protocols also require persistent sessions, right? If your BGP session goes down, your routes are withdrawn, your node is gone. And more importantly, deletion is always hard. You never really know when you can delete the pod CIDR because you need to delete the pod CIDR when the node goes down. But CNI doesn't tell you when the node goes down because the node's gone down. All right, so that's what CNI and the CNI infrastructure is expected to provide into Kubernetes. Now I'm going to talk about some best practices for operators, the best practices for users of Kubernetes, because it is still a little rough around the edges. There are still a lot of gotchas. The first best practice is to understand how the kubelet is configured for CNI. So this is a bit of a pop question. This is a bit of a quiz. Which of these command line flags tells you which CNI configuration file to use for the kubelet? Does anybody know? None of them. It doesn't take it. The kubelet does something that seems insane, but is actually for a very good reason. And that is the kubelet scans a directory every 5 seconds and picks whichever configuration file has the lowest ordered name. It keeps scanning and reparsing forever. So the first best practice is to only ever write one CNI configuration file to this directory. A corollary is to don't test in production. If you want to test this different anyways. Why does it do this? It does this so that you can start the kubelet and then use a pod to deploy a CNI configuration file. So it seems a little awkward, but in fact, there's a very good reason. Right now, you have this nice decoupling. Comes at a bit of a cost, though, which is if you accidentally write 2 CNI configuration files to disk, you may get yourself into a bit of a race condition where you parse b.conf, add a pod onto the B network, then you drop in a.conf, and you try and delete the same pod in the A network, and it goes, huh? So first best practice, only write 1 to disk. This has caused production outages. Don't do it. The second thing is to understand some of the new changes in CNI. CNI now supports something called plugin chaining, which is a really powerful tool for you if you want to tweak your network. Plugin chaining executes multiple plugins for a single container. It executes them in a row, and it passes the result of the previous one into the next one. And what this means is that if you, as an operator, want to do something very simple, let's say that you want to tag all of your pods with a certain QoS class. It means that you can write a small amount of Go code, call it 100 lines of code maximum, to accomplish this without having to know how to write a full CNI plugin, without having to know how to write a full interface plugin. Plugin chaining means that you can adjust your network, means you can tweak your network with a few JSON changes as opposed to building a whole new binary. There are some existing production plugins now that rely on plugin chaining. The big one, the first one that really motivated this was host port forwarding. Any of you want to have something listening on port 80 on the host, you need to do port forwarding. You can write in a second plugin in the chain that just does host port forwarding. Otherwise, it's entirely interface agnostic. Also, you can tweak sysctl parameters, right? This is sort of a typical CNI configuration file. It might look something like this. It's a bit extreme, but only the first one creates the interface. All of the other ones might adjust firewalls, might adjust sysctls. And like I said, these are really easy to write. We have a skell plugin that you can copy and paste, and 100 lines of code, you can do almost anything you want and adjust your network. Another best practice with CNI is to self-host. You know, we need to run a daemon on every node, and man, like, does anyone know how to run a daemon on every node, right? So you should deploy your plugins using Kubernetes. This takes a little bit of subtlety to get it to use the binaries. Your manifest needs to do this sort of funny dance where first thing they do is install and activate the routing daemon. Then they copy the plugin binaries onto the host into a configured directory. And then they copy the configuration file. And it's really important that the last thing you do is to copy the configuration file, because copying the CNI configuration file to disk is the secret signal that says to the kubelet, the network is up, and you may now start pods that are not host networking pods. This is a little bit of an awkward API, but this is the API that we use to say, yes, the host is up, give it to me. Some important things to get right when you're writing these manifests, especially for the daemon. This might seem obvious, but it should be said. You need to run the daemon in the host network. You also need to make sure that your daemon ignores all taints, because master should be able to reach pods. Master, in fact, has to be able to reach pods. So you definitely need to run your routing daemon on master. And this is a little bit of a funny tweak. You should use the magic grace period here, which will let you restart your daemon very quickly, minimizing the amount of time that your daemon is down in the event of an upgrade or a crash. Now, most of your vendors will provide a manifest file for you that will do this automatically. So you shouldn't necessarily have to write these, but you might want to check and make sure that they follow these best practices. Another best practice that requires a lot of careful thought is disaster recovery, especially if you have a self-hosted control plane. You need to understand the dependencies that your CNI plugin has. You need to always run your API server as well in host networking, because if your API server is down, nothing may start. And you need to understand the exact dependency chain and make sure that your daemon set, your routing daemon, will start up without any other running services. In systemd, if you have a dependency, systemd will very happily tell you that a transaction is not achievable, right? It will tell you, nope, can't do it. Whereas the Kubernetes general practice is to just, if the conditions are not met for whatever your conditions are, retry. So you'll never actually get any sort of failure. All you'll know is that all of a sudden your control plane is down and you have no idea why, and you have no idea how to start it. So be really careful. Think about this very carefully. All right. Yes, exactly the time. So now that's best practices for run executors, but this is KubeCon. We are Kubernetes developers. And so I'm really excited to talk about best practices for plugin developers. A lot of these slides just come from questions and discussions we've had in the various Slacks. And I think there's a lot to learn from this, even if you're never going to develop a CNI plugin. First of all, because A, you should develop a CNI plugin because they're awesome and really easy. And second of all, I think it's important. One of the values of coming to a conference like this is that you get to meet the maintainers and you get to talk about the sort of things that they're worrying about, and you get to understand why the software that you're running is built the way it is. So I think it's really great. I love hearing about people talking about all sorts of difficult things to develop because I really learn a lot, even if I'm never going to go into that world. So jumping in, what are the best practices for you to write a CNI plugin? The first thing you need to do, and we should all really do this, is to understand the life cycle of pods and the kubelet and how things are executed. The kubelet is massively parallel, has hundreds of Go routines, and it has very few guarantees. It gives you exactly one guarantee in the world of CNI. CNI has the notion of CNI has the notion of a container ID, some sort of UUID, free text field that identifies a container. It's a meaningless thing. It's expected to be routed by the runtime. The spec requires, and the kubelet does guarantee, that you're going to see exactly one add request for each CNI container ID. And this is the only thing you can rely on. You cannot assume that you will see a delete a short amount of time after a sandbox or a pod is deleted. You can't assume that you'll see a delete before the node has been rebooted. You may see the delete after the reboot. You might not see a delete before you've got a crash looping pod that runs 1,000 times and you run out of IP addresses on the node. No guarantees. And you might not see a delete ever because your node might get chaos monkeyed or have a bad disk or go into space. So you need to be prepared as a CNI plugin author to garbage collect resources externally. And a really common best practice is to store state that dies after a reboot in /run. Really simple, guaranteed post-reboot delete. If you use any other identifier as your primary key, it might be reused by the kubelet. You cannot even pod name may be reused. This has caused production bugs in commercial CNI plugins. The race condition is something like this. If you have a pod with the same name but two different pod IDs, add A1, A1 crashes. At some point in time, the kubelet is going to restart it, and it might restart it and do an add of A2 before it does the delete. You delete A1, but if you're using A as your primary key, A2 is now offline, right? All this comes from you need to understand how the kubelet works. The second thing you need to understand is you need to understand the host network, the host networking environment. Kubernetes generally expects that all packets leaving a pod traverse the host. And this has a lot of subtle implications. So most plugins, for reasons of efficiency, do all of their work in the host's networking namespace. For a lot of reasons, right? Duplicating functionality, duplicating IP tables rules, duplicating routing tables rules, and every single pod's networking namespace would be a waste. This is all non-pageable memory, right? And more IP tables rules, more traversal is a waste of time and energy. There's also a requirement that host networking pods be more or less equivalent, right? So anything that a non-host networking pod can access, a host networking pod should also be able to access, right? They should be uniform. And also in some cases, it may be that if you're programming the pod's networking namespace, it's a little bit of a leak, right? You don't necessarily want to set up your service rules for every single service inside every single pod, because now those pods can enumerate all your services. So you have to program the host network. You might as well only program the host network. Not only in CNI, but also non-CNI functionality is also generally only implemented on the host network. So kubeproxy, love it or hate it, kubeproxy does what? It does DNAT. It rewrites destinations. These rules are almost always only installed in the host's IP table space, right? It uses IP tables, or now it uses IPVS, which is awesome and really high performance. It only does this in the host's networking namespace. Most network policy providers also only program their firewall rules in the host's IP tables namespace. Traffic shaping and overlay networks, of course, if you're programming a routing table, you only want to do it once, so you do it in the host networking namespace. So once you understand what the host's networking namespace, what is generally done inside the host's network world, you can decide whether or not you want to give it up. You can choose to re-implement this. For example, Cilium re-implements all of this in BPF. Or you can decide that I don't care about this. Now that you know I don't care about this, I want to do something. I want to connect my container directly to the network. This works really well. It's really fast. It's very high performance. You can do Mac VLAN. You can do SRIOV and pull off and give it a chunk of a PCI device. And so the lesson from all of this is that, as with all systems, you can take these nice clean abstractions and you can give them up a little bit in exchange for speed. You just need to understand the trade-off that you're making. The third thing to be aware of if you are a plugin author is to be wary of hairpin. Now, hairpin is anytime a packet goes back to its destination, and CNI plugins must handle these two cases. Kubernetes must be fully connected. So you have to handle anytime a pod talks to a service, talks to a pod on the same host, and you have to handle anytime a pod talks to a service, talks back to itself. And this has caused production outages, and it was my fault. Yeah. So how do you solve this? The solution, if you want to talk technical, the solution is to masquerade the source IP address. But the real solution is to make sure that you have a test case for this. If you're CNI plugin author, make sure you test for this. If you are evaluating CNI plugins, make sure that your acceptance criteria includes this as a test. Otherwise, you will get bitten. Some CNI plugins, this does work only if you configure it in the correct manner. So you absolutely need to test for this when you're evaluating your CNI plugins. And the fourth best practice, if you are a CNI plugin author, is to use this cool new feature that came with CNI. It's only a year old, called capability arguments. So the kubelet now will fill in dynamic configuration into the CNI configuration file. Previously, it basically just copied the file from disk and spit it right out directly to the plugin's standard in. This is really awesome because it means that you can reduce your dependency on the API server, which means that you have less of a bootstrapping problem and you have higher performance. Capability arguments are defined in the CNI spec and need to be implemented in the kubelet. The current capability right now is host port mappings. In other words, host port mappings is defined in the pod spec, and Kubernetes will automatically put that into each pod that has port mappings installed. Future capabilities that are going to be coming with probably Kubernetes 1.12, maybe 1.11 if we get our stuff together, is going to be passing the pod cider inside the network configuration and bandwidth limits inside the networking configuration. And the real goal of the CNI project is to be able to get up a pod using Kubernetes, bring up a Kubernetes pod without having to talk to the API server at all. Right? This is any sort of dynamic configuration that Kubernetes passes, we should be able to represent in our configuration file. So if you find something where this isn't the case, file a bug, and we will try and fix it. Capability arguments look a little bit like this. This is the structure on disk. You need to flag, as an administrator, writing your configuration file, you need to flag which capabilities your plugins are capable of. Your vendor should tell you this if you are using any sort of vendor manifest. And the reason we do this is that we don't necessarily want to care in the Kubernetes side about how port mappings are implemented. That depends on if you're using BPF, that depends on if you get to pass through the host's IP tables. Right? Kubernetes can make no assumptions as to how this can actually be accomplished. So instead, Kubernetes only can see if a particular configuration declares that it supports port mappings. So if you say that my configuration has a port mapping capability, what Kubernetes will do is the standard in that is passed to the actual plugin will have this section replaced with this, the runtime config with the port mapping key. And that will contain the dynamic information from the API server. Another best practice for the developers is to be aware of plugin chaining. I mentioned it on the administrator side. Plugin chaining is awesome. Plugin chaining is a great way for you as an administrator to write a very simple plugin that does just what you want. Plugin chaining is also super useful if you are a networking vendor because it means that you can now expose your functionality as to something you provide, say firewall rules, without necessarily having to dictate the entire networking stack. It allows you to be flexible and it allows your plugin to be more available to more customers. So this is super common for post-setup tweaking. This is how it looks. This is the CNI plugin this is the CNI configuration file on disk. And then this in green is what your binary is actually going to see from the kubelet. You can see there, I'm imagining the second plugin that's going to be executed. It executes them in row from top to bottom. This plugin is called iptables_allow. And what that plugin is going to see is it's going to see its configuration, and it's also going to see the previous result from the previous plugin. And this is really cool because now you can do things that rely exactly on the previous result. You can do things like, in this case, this plugin is going to add an iptables rule to allow either this interface or to allow this IP address. This is something you can only do with dynamic plugin chaining. The details of this specified, but important to understand that the plugins are executed first to last, and the previous output is passed to the next one, and only the last plugin dictates what kubelet understands to be the IP address. So the last plugin writes the result back to the kubelet. Now, for delete, plugins are run in reverse order. This is a problem with the spec as written, which is that the plugin that runs last gets to know the IP address on add, but it doesn't know the IP address on delete. So we're actually fixing this in spec 0.4 with essentially cached results. So this is going to be a lot more usable if you're writing a plugin in, I think 0.4 is going to be released in the next month or two. So what this means, what I really want to emphasize for networking vendors is that if your plugin only touches the host side, or if it operates in a mode where it only touches the host side, then it can easily be a chained plugin, right? And for example, imagine a firewall plugin, let's say Calico, right? Calico is a network policy provider, but Calico could, it doesn't right now, hey Brian, it doesn't right now, but it should be able to, for example, say work with virtual machines. You should use chain plugins to allow administrators to swap out the connectivity plugin, whereas you can provide perhaps your policy or reachability plugins separate from connectivity. Cool. There's a lot of information, but I kind of wanted to get technical. Very briefly, I'm going to talk about what's next. CNI 0.4 is going to be released in the next month or so, and the big thing that it has is a get verb, result caching, and more capability arguments. Get has wound up with a lot of corner cases, so it took us a really long time to figure out how to do this exactly correct. The spec language still needs a little cleanup. The big one is result caching, which shouldn't matter to most administrators, but it's going to allow chained plugins to provide a lot more functionality and for them to not necessarily have to write state to disk. If anybody's writing state to disk, it should be the runtime or a stable layer. Also coming soon is CNI 1.0. Hopefully it will have no new features. Hopefully it will just have a better specification. What's next? IPv6. CNI has supported IPv6 for years. Kubernetes has not. Kubernetes has alpha IPv6 and 1.9. Dual stack support is sort of being designed, but not a lot of progress has been made on that yet. Still a lot of work to do. Still looking for contributors. Still looking for people to review the design. A big one that everybody wants, that everybody in this particular community is working very hard on, is multi-networking. CNI always has been and always will be a single network per configuration file. More or less, there should be one interface in your pod for a single network configuration file. However, there is a use case. There's lots of use cases for multiple networks. There is a CNI pseudo plugin right now that will just execute multiple CNI plugins. It's a bit of a hack, but it has wide adoption. And that tells us that we need to do a better job of supporting this in Kubernetes, right? So there's a lot of things to figure out in this design, a lot of subtle questions that need to be answered. For example, will pods always have this default network? Will pods always have this a.conf? And the answer that we've decided on is yes. Pods should assume that any additional CNI configurations that are executed will be additional. There will always be an ETH0. This will be directly connected to the node. A big question that we've decided to punt on for now is how to expose additional interfaces or how to expose additional IP addresses. If you remember way back in the beginning, pod IP was a single object. That is not changing for now. So you will need to use these endpoints manually. That problem is not going to be solved for you right now. This might change. We're looking for good solutions for this. What about security? No idea. Not on the plan for right now. There is no plan as of yet to include this in for something along the lines of pod security policy. So if you don't trust your administrators, if you have access to a network that you think is need to be secure, that is not yet supported in the current draft for multi-networking. And then what about hairpin? Good question. We haven't figured it out yet. Part of the multi-networking approach, part of the multi-networking working group is also seeking a way to combine device plugins. So the device plugin interface inside Kubernetes, combine that with multi-networking, right? Makes a lot of sense. There's a lot of common features that could be thought of, functionality that should be shared, right? Device plugins allocate a device plugins manage schedulable resources. None of these things are in CNI. CNI knows how to initialize a network. CNI knows how to hand an IP address back to the kubelet for it to expose, right? So there is a sort of an interesting daemon right now that works entirely with annotations. If this is something you're interested in and getting it into core Kubernetes, join SIG Network because this is in design and this is a really cool feature that's coming. So what's next? Really, that's up to you, right? This is a wide open community. We take lots of pull requests. We have hundreds of contributors. We're going to have a meet the maintainers later today. It's an active specification. There's lots to do. So I'm really excited. This community knows so much. There's so much more we can do. Networking is really complicated. It's really diverse. And I'm really excited to see what's next. So thank you so much for sticking through these technical details. Are there any questions?
When you change the CNI configuration file, which is detected by the kubelet, when will those changes propagate the actual interfaces, if at all? And should they do it out?
So the question was, what happens when you change the CNI configuration file on disk? What happens how are those changes propagated? And the answer is, for existing networks, for existing interfaces, those changes are never propagated because there is no change verb in CNI. Essentially, only all new interfaces going forward will have the configuration changes. So if you change your configuration file in a substantial way, you should just reboot the node. Yes. Okay, I know I'm late for lunch. Oh, well. So CNI is used by Rocket, it's used by Mesos, and it's used by Cloud Foundry. Yep. All right, thank you very much. Enjoy lunch.